Um, Welcome everyone. Thanks for being here. Welcome to the December edition of the AI Fundamentals and ELLIS Unit Manchester Invited Speaker Series. And today we are very pleased to welcome Sam Powell from the University of Bristol. Sam works generally on inference, computation, probability, and statistics. And he's going to tell us today about a state space perspective on modeling and inference in online skill ratings. Sam, the floor is yours.
Thanks a lot. Thanks for the invitation. Thanks to everyone for being here. So I'm going to talk to you about a project that I did with some friends over the last couple of years. It's now sort of published in a statistical journal, and there's a software package associated to it that my coworkers have sort of done some hard work on, let's say. So let me just see if I can click through. So big thing to flag at the start. So all of this was done with my collaborators. So Sam here is now in industry working for a sort of AI hardware company called Normal Computing, doing lots of very interesting stuff there on simulating diffusions. Lorenzo is sort of, he's now faculty in Italy and works a lot on state space models for epidemics and stuff like this. So we're all sort of trained as statistics and signal processing type people. But yeah, it was a very fun collaboration, and a lot of the credit goes to both of them as well, let's say. So this is what the paper looks like somehow. Now, the first thing I like to do when giving a talk, particularly when there's lots of unfamiliar faces in the audiences, is to let you know that you should really stop me at any stage if things are unclear. If it's not clear why I'm doing things the way that I am, this goes double for younger people, let's say PhD students. Definitely don't feel afraid to ask me a question. The general principle somehow is that if you don't know me and I spend 50 minutes confusing you, it's not much use for any of us. So let's try avoid that collectively, let's say. Okay, so I'm going to jump straight in by talking about what the central object of study in this work is, which I'll call the skill rating problem. And we'll think of this in the context of things like sports, okay? So let's think about competitive sports and sort of prediction tasks. Now, for the purposes of today, a sport, quote unquote, is some sort of sequence of events involving players playing against one another in matches from which we observe results of matches, right? And so for the purposes of today, the players are the different agents who enter into a match, which could mean an entire team in the case of a sport like football, for example. So it's easiest for us to think of there being as two agents going in, they play in a match, we observe who wins and who loses. Maybe we observe a score line or other responses. It's sort of a very simple model, right? And so in the context of this, right, a sport certainly includes things which I think are uncontroversially sports, like tennis, football, basketball, and so on. It also, sort of following the definition, it includes things like chess and online gaming, where it's a bit more controversial whether you count that as a sport down at the pub, let's say, but for the purposes of this talk, it definitely counts. There's also other interesting examples which are much less obviously sports. So things like apps for learning a language, they have the same structure, where you have two different types of player. You have the student and you have the question. And somehow what happens is that they compete against one another to see if you can get the question correct. And so some of the things we say today will be equally useful for that sort of thing. And this last sort of emoji there is a relation to something I learned recently, that many of the sort of rating techniques we'll discuss today are also used behind the scenes in various dating apps. I'll let you interpret that for your own sake, but it's sort of, the point is somehow that the framework is useful in various contexts, okay? And so a basic task in these sorts of models would be something like the following, given past results of some competition, predict future results. Okay, that's sort of fundamental, it's prediction, it's all observable, you can do it however you like, somehow. But a more refined task that might be interesting for inferential purposes, but also for asking more interesting questions than just prediction, would be to do something like inferring the skill of players in a competition, right? Somehow to unpack the latent structure of the competition beyond just looking one match at a time, let's say. Okay, and so there's various applications to this. A simple one would be something like seeding a tournament. So you're the person who's in charge of setting up the draw for the Wimbledon tennis competition. You want to set things up so that the final matches are interesting, let's say, and having some understanding of the relative skill of players is useful to this end. Team matchups are sort of a similar consideration here. So one thing to have in mind would maybe be something like an online gaming system where you have, 10 people will log on. You have to allocate them into a team of 5 and a team of 5 so that the match is relatively competitive. Otherwise, there's no point playing, right? And so having some understanding of skill is very useful there also. And then a sort of more statistical or sort of experimental design type perspective would be things like evaluating interventions. Okay, so what I mean by this is, if you're able to resolve the skills of players within a team or different factors within a team, you can begin to ask questions like, if I substitute out this player and replace them by someone else, what can I expect to happen? Okay, or if you want to fire the manager of your football team and replace them by someone else, you can try to be principled about that by, estimating their impact on the team. So things like that. Now, the idea is somehow that, okay, if you just care about prediction, you might be able to take a more direct approach, but somehow if you're interested in more refined queries, you might want to understand things in more detail. Okay, so a good thing to start off here is a sort of non-mathematical observation, which is that this is a problem that lots of people care about, and I would say upwards of 95% of them are not mathematical by any means, and not really interested in being mathematical about the project. Trying to figure out what will happen in a football match, for example. Certainly I would first turn to writing down a model and doing statistics with it, but I realize I'm pretty unique relative to the whole population in that sense, right? So, the different approaches you can take can be very non-mathematical, right? It could be I go on Match of the Day and I chat to people about football, right? I can do things that are sort of mathematical, but maybe only vaguely statistical, right? I can do things where, I write down some loss function for some predictive model, I optimize the parameters of it, and I use that to make predictions. But maybe I never write down a proper statistical model for what I'm doing. I just write down the function that takes inputs and gives outputs and outputs. This would be sort of an applied math way of doing things. And then you can go fully statistical, if you like. You can really write down a model for all of the moving parts of what you think are happening in a sports competition. You can give it parameters, you can try to fit those parameters and then do uncertainty quantification and everything on top of that using classical tools of statistics, let's say. And so because of my training and my interests, I prefer the third one, but it's certainly not a universal thing to do. And somehow the important thing to do is to think, okay, what are your goals? If you're entertaining doing something for this problem, actually what's important to you? Is it just prediction? Is it some deeper level of understanding? Is it decision making on top of that, and so on? And you can, if you're asking less, you can get away with doing less inferentially. Okay? So let's give an outline of what our approach is going to look like. As I said, it's going to be rather model-based and mathematical, but very flexible on top of that somehow. So what we're going to do is start off by writing down some very general mathematical models for the skill rating problem that are going to be sort of flexible enough to make sense for different types of sports, but have parameters attached to them which will necessarily be different for different sports. Okay? So we're going to give those models statistical parameters and try to fit those in some capacity. Now, for the skill rating problem, it's not a completely general statistical model where you can have whatever likelihood you like. Somehow there's a lot of structure to it that we want to latch onto. And so we're going to work with a specific class of models called state space models. And I'll give a sort of introduction to those momentarily. But what's special about state space models is that there are specific inference problems you have to solve when resolving a state space model that you don't have to worry about in the context of something like regression or clustering, let's say. Okay, so we're going to talk about what those inference objectives are, and then we'll talk about algorithmic ways of solving those problems. Okay, so this is sort of the layout of the talk as much as it is of the project as a whole. A sort of thing I would like to highlight maybe is the focus of the way we're doing things. It's on the high-level modeling framework for how what the ingredients of the model are that you need to specify to get something working. We're less concerned with the specific low-level details of how that model is specified. In the following sense, I will write down sort of, models for dynamics and models for observations and stuff like this, and you will very reasonably look at some of them and say, I don't really like this likelihood very much. I would rather do something else. And the likely situation is that I will agree with you. Okay, the point is to be illustrative and show how things work and where it's flexible, rather than to say, I think this is the best way of modeling everything, at the granular level. Let's say. And you'll see what I mean shortly. Okay, so this is kind of the workflow. Right? We sort of write down some general mathematical models which we think capture the structure of the skill rating problem. We're going to equip those with parameters that we can try to estimate. These will take the form of state space models. And so the key things to do are to sort of remind us of when we're trying to fit a state space model, what are the tasks that come up in doing that? They're sort of quite specific, but also well established. And then we're going to solve the inference problem for those. And there's some specific challenges that come up there. Okay. So before getting into state space models, it's useful for me to start with the notion of a latent variable model, which is somehow the baby version, if you like. So let's start with the sort of conceptual warm-up here. So suppose I say, given two players of a sport, predict the outcome of what's going to happen between the two of them. What influences the result of the match? Okay, and let's say I don't give you any more information than just which teams are involved. I don't tell you the weather, I don't tell you where the match is being played, and all those sorts of things. So first order, a reasonable idea would be to say, okay, the probability that one team wins rather than another, it's a function of the skills of the two teams, okay, in some abstract sense, right? Right, and so the idea would be then, okay, mathematically, something I can do is I can, assign some latent variable to each team which quantifies their skill, and I can use that as the basis for picking up a mathematical model. Right, so for each player, which I'm going to index by I, we're going to give them a skill level xi living in some set x, which is usually going to be the real numbers or something like the numbers from 1 to 100. Something with an ordering structure where there's some meaningful way of saying this player is better than this player. So given that, we might say a simple model would be if I have player I and player j playing against one another, the probability that the first one beats the second one is just a function of their skills. Okay, maybe with some additional hyperparameters cooked in, but already this is pretty flexible. Right? You can imagine there's various sort of structural constraints you want here. You probably want that this function f goes up when the first argument goes up and goes down when the second argument goes up. Somehow you want it to be monotone in skills, if you like. Okay, so that's a starting point for us. Now, state space models sort of come, you can motivate them in various ways, but it's somehow, I think of them as enriching this basic model. Right? So in what we started with, right, we have just a fixed skill level for each team. And the very natural question is, okay, should a player's skill level be something that's static in time? Because we know that the way that competitions take place, it's not that 10,000 matches take place in a single instant, it's that they go sequentially somehow. Okay? And so you can ask the question of, okay, if my data arrives sequentially, should my model account for that structure somehow? So if you look at this question, I mean, it depends on what sort of competitions you have in mind, but I think for many people, a natural answer is probably not. Okay, there's sort of various competitions where we have this notion of the form of a team or player, which is something that varies over time. And so it's tempting to put it in just on those principles. But actually, a slightly better answer from my point of view is actually you can write down a model at some level of granularity, and you can let the data decide. Right? You can write down a model which has the capacity to have static skill levels and dynamic skill levels, and you can see how much the data want to include this dynamism. Okay, and so as a sort of empirical fact about the world for many sports that we care about, it is useful to have these skills varying over time in some way. Okay. So I can't sort of put maths to that, but that's what we see to be the case. And so when we decide to put some dependence over time, if we think of being completely flat over time, the simplest way to deviate from that would be to have some local variation in the skills according to a Markov chain, basically. So the idea is, your skill is not constant, but what happens is, it changes from one day to the next in small ways somehow. Your skill tomorrow only depends on your skill today, and we're independent of everything that came before that. Okay? And so when we do that, we go from a latent variable model to a state space model. This is what people mean by a state space model, roughly speaking. Sometimes you'll hear it called a hidden Markov model instead, or a hidden Markov chain model, but it's structurally the same thing. Okay, so this is going to be our building block. And so what does a state space model look like in one slide? This is a picture I'm sure many of you will have seen in some capacity. So, we write down, if we write X for our latent signal, the sort of skills of the players, and Y for the results of the matches, right? We're going to have that our model for the player's skills is evolving as a Markov chain in time. You sample your skill at time 0, conditional on that, your skill at time 1 is generated, conditional on that, your skill at time 2, and so on and so forth. Okay, and that's what these M's are. They're sort of conditional distributions, if you like. And then on top of that, we have our emission model, for the observations here, where the idea somehow is that the outcome of a match taking place today between two teams depends only on the skills of those two teams today. Okay, we forget about their form last week. Everything is captured in their skill today. Okay, and so the sort of graph that goes along with this is the following. So somehow the illustration is that up the top, you have the X's evolving in a straight line with no additional dependence, sort of what the arrows are entailing, and then the emissions are coming down depending only on the scale at the relevant day. Okay, so it's sort of the simplest model for this kind of a thing, where you include this kind of dependence. And these are very well studied, particularly in sort of engineering and systems control and these sorts of things, but also in statistical modeling more generally. Right? The idea of having some unobserved signal which you see in noise is sort of ubiquitous. Right? Okay, so we're sort of interested in this class of model. Now, for us, in the case of skill rating, this model is true, but writing it this way obscures the structure a little bit. So for us, this state vector x, it's really the skill of all players in the system. Right? We have to track all of those skills to have a complete model. And so we potentially have a very high-dimensional latent state. Right? Even if you think, say I'm looking at the Premier League, which has 20 football teams in it, and for each of them, I store a skill rating between 0 and 5, let's say. Very quickly, I have a state space of size 6 to the 20. Right? And so working with probability distributions of that size is rather challenging. And so there are some specific structures we're going to use to make life easier for ourselves. Okay? So this is sort of a version of the curse of dimensionality. Specifically for state space models, it makes life very difficult. It makes all sorts of inference algorithms very difficult to run efficiently or accurately. But we have some sort of antidote to the curse of dimensionality here, which is that it's a reasonable assumption that the skills of different teams, they don't really interact unless you're playing a match against one another, right? Unless you knew for a fact that teams were training together or there was some other sort of interactions taking place. It's reasonable to sort of decouple these somehow. And so with that in mind, it's natural to model the skills of the players not as evolving as one big sort of lumped together Markov chain, but independently across players. Okay, and this is what we call a factorial state space model, also factorial hidden Markov model. Okay, so these have been sort of studied explicitly since the mid-90s or so, but conceptually it's a very natural thing to do. If you want to study a high-dimensional system, start by studying the case where lots of things are independent of one another. Okay, so this is interesting, but still doesn't get rid of our challenges entirely. Another point that's also worth making, let's say, so this is what I say at the top, that's about the dynamics of the model, what happens before we see results. There's also the fact that the observation model is very sparse, right? Even if we have many, many people in the competition, each match involves 2 teams or some fixed number of players, let's say. And so, when we see the result of a match between 2 teams, it doesn't necessarily affect our beliefs of what's happening with every single other team. So there's some sort of sparsity there, which will make our lives easier. So we have complete decoupling in the dynamics and sparsity in the observation model. And so visually, things look much the same as before, but with some sort of slight tweaks. Right? So if we look at the dynamics model here, it's the same as before, but now factorizing across individuals as well. Right? You have a Markov chain in time independently across the population, and the observation model is much the same as it was before, but sort of factorizing across matches within each game, let's say. Okay, and so the graphical representation is similar to before, but with even more, let's say, with even more vertices, but even more sparsity in relative terms, right? So up here we have, the skill of team 1 evolving, the skill of team 2 evolving, 3 and 4. Okay, on the first match day, teams 1 and 2 play one another. On the second match day, teams 1 and 3 play each other. And on the third match day, teams 2 and 4 play one another. Okay, so we have lots of vertices, but very few edges relative to that. So we have a lot of sort of sparsity structure. And this is going to be our main object of study. Okay, how do we sort of conduct inference in these models? So this is all pretty abstract. This doesn't really say the dynamics have to be one way or the other. And so just to have some firm things in mind, I want to give some examples. Okay, so for dynamical models, if we decide to model skills as being real numbers, right, a very common choice is to evolve skills as evolving over time according to something like a random walk, right, a Brownian motion, let's say. So the idea is, given your skill today, your prediction for your skill at some point in the future is just adding noise to it in some way. And as the time horizon goes to infinity, you become more and more uncertain about the skill level. Okay, so this is very nice to work with because Brownian motion is a Gaussian process, so lots of computations become very straightforward. Computationally, this is very nice. From a modeling perspective, it's a bit peculiar, right? Because you have that skills are sort of non-stationary over time, and you can predict that the best player a year from now you expect them to be much better somehow than the best player today. And whether that's natural for your sport is kind of model dependent, but it is sort of validated in some cases. I think people would say the best chess players these days are noticeably better than they were 50 years ago. Nevertheless, if we rather have something with more sort of stationarity and mean reversion properties, where the sort of typical skill is always of order 1, no matter how far into the future you go, you can use something like what's called an Ornstein-Uhlenbeck process, which essentially is sort of a process where there's a bit of noise being added at any instant in time, but you're sort of drifting towards the origin, typically. So that sort of stabilizes things nicely. And again, it's a Gaussian process, so doing computations is very nice. And there's various sort of exact formulas for things you might care about here. Now, if you prefer discrete state spaces, and this is somehow how the project actually started, you might say, okay, if I look at various sports games, you would rank teams or rank players just with a number between 1 and 100. Okay, so think of the S as being not tiny, but not astronomical. Okay. In that context, it's very natural to say, okay, the simplest thing to do is to again have sort of random walk dynamics for the skill. Okay, my skill is sort of constant through time, but occasionally I jump up by 1 or back down by 1, and so on. Okay, and the sort of frequency at which those things can happen is captured in this parameter lambda naught. But again, it's something very tractable where there's lots of computations we can do. These definitions at the bottom, the only subtlety they're saying is if you're already the best you can possibly be, you can't become even better than that. You can't jump from 100 to 101. And similarly, if you're at the bottom, you can't go negative. Okay, so these are some choices you can do, which would sort of be a very simple baseline. For observation models, there's various things you can do. I think I will mostly focus on sort of binary observations, which is to say where all you see is this team 1 versus this team 1. Okay, so we have sort of binary observations, and so a natural thing to do would be to do something like what I would, as a statistician, call a generalized linear model, something like logistic regression. Okay, so you have your sort of continuous skills for players. So given a home team and an away team, the probability that the home team wins is obtained by looking at the difference in skills between the two teams. That gives you a real number, and then you pass that through a sigmoid function to get a probability. Okay, this is sort of very, very standard. So the logistic choice is sort of historically most prominent, but we'll see later some examples where using sort of the probit regression version of things is a bit nicer, essentially to do with some sort of Gaussian conjugacy properties you might be interested in. Okay, so that's sort of very common. For discrete state spaces, you can do the same thing, right? A discrete skill between 1 and 100 is still a real number, so you can apply the same formulas if you'd like. But you have a bit of extra flexibility, which is that you can actually just parameterize these win probabilities directly, right? There's 100 possible skills for the home team, 100 possible skills for the away team. So you can just fill out a big 100 times 100 grid of probabilities associated to that with some sort of natural constraints to make sure that they're monotone in the ways you would expect. So there's sort of lots of flexibility here. Now, if you wanted to extend to richer observations, like having a draw option as well, it's very natural for football and other things. It's pretty straightforward to do this. Statistically, we would say it's the difference between doing binary regression and ordinal regression, right? Where there's sort of some ordering between the results that you can have. Right? And if you want to have things like, the score line of a sports match, again, you can do this using some interesting Poisson type distributions. I won't sort of linger on the details because most of what we do will still be quite generic at that level. Okay, cool. So let me talk a bit about inference in state space models because it's sort of a key consideration and motivates a lot of the developments we have after this. So inference in state space models has the following features. Somehow, if we go back to real tasks, what are the things we might be interested in doing concretely? These are not all the things, but there's some of them. One would be to predict in real time the outcome of current matches. If you want to do betting or something, that's a sort of very natural thing to do. Now, on the basis of our model, what information do we need to do that? We need to know what is the skill level of the teams who will be playing today? Okay, given the information so far, what is their skill? And so that's, for us, we want to compute the distribution of the skills on match day K, given the results of the matches in the past. Okay, and this is what we would call the filtering distribution. Okay? So that's sort of the sufficient information for solving that problem. Now, another thing we might want to do is evaluate the past performance of players. Right? Go back and say, okay, if we go back to January, everyone was criticizing this team for behaving poorly. Was it that they were genuinely a worse team, or is it something you could put up to a bad run of form, or the luck of the draw, let's say? And so that sort of retrospective evaluation involves this distribution, where we're looking at the skill at a given time instant, given an even bigger amount of information. Somehow, with capital K being much larger, we're conditioning on a bigger set of information, looking back at the past and saying, what was going on there? Okay, and that's something we call the smoothing distribution. One way of thinking about the name there is somehow that because you're conditioning on more information, you had sort of more certainty about what was happening in the past, and things tend to evolve more smoothly once you condition in that way. And finally, probably the most important one in practice is, these models that we write down have parameters in them which we don't know, right? This is not something like doing filtering in a physical system where we know what gravity is and we know what speed something is traveling at. The skills that we're working with, they're not directly observable, and so we have to fit a model to them, directly ourselves. We have to do that by our hands. And so to calibrate those parameters, we somehow need to estimate the likelihood of the model as a function of those parameters and to optimize that. So we need to do some combination of likelihood computation and parameter estimation, which is sort of very closely tied together in our usual setting. Okay, so there's something peculiar here, which maybe some of you will be familiar with, but I think it's sort of instructive to discuss, which is that, yes, sorry.
I had a question about the smoothing definition that you have.
Yep.
So often, I would like to say that if I have y observation on a force grid, and I want the x on a final grid. Is that part of smoothing?
So the distinction is really whether you're conditioning on information up to the present or information including the future as well. In terms of the coarse fine thing, I suppose it depends on...
let's say y is at t equal to 1, t,
yeah.
y, 7.
Yeah, and you want to look at 1.5. Or, okay. Yeah. So that would be... That would typically come under smoothing. Yeah. And that, it's much closer to smoothing. Certainly. Okay. So, even if on paper you only care about one of these, say you're just going out and out prediction, the reality is that they're quite intertwined, right? You can't really decouple these three tasks. So if you want to do good filtering, right, you need to have good parameter estimates. Because if you're computing conditional distributions relative to the wrong nominal model, they don't really mean anything, right? You're sort of misspecified. And so there's sort of work to be done there. If you want to do good parameter estimation, you need to be able to look at what has happened and sort of attribute responsibility to the parameters in some way. And we need to do smoothing to accomplish that. We need to be able to look back at past information and understand it somehow. And that's effectively what the smoothing distribution computes. And to do good smoothing, we need to do good filtering, right? We can't look backwards without having looked forwards first, somehow. And so you have this sort of intertwining between the three of them, which means that in most cases, or in these specific cases we'll talk about today, let's say, you really need to try solve all three of them at once. Okay? There are worlds where you can get away without something. As I said before, there are cases of physical systems where you really know the dynamics very well a priori. But for us, the dynamics are made up anyways, somehow. So we really are responsible for all parts of this. Okay. Now, in factorial state space models in particular, we have some additional challenges, because remember that our latent state is high dimensional but decoupled. Okay? So, as I hinted at before, the fact that we have high dimensions means that even representing these tracking distributions is tricky, right? Again, 5 or 6 skill levels, 20 teams is quickly an exponential number of just numbers to store somehow. Now, the reality of the situation, as you'll see in the literature and sort of related problems, is it wouldn't even be super useful to track the full filtering distribution of all teams at once, because it's very unlikely you'll need to know the correlations between several teams at once, let's say. As we sort of established, 2 teams play one another at a given time, so most of the reasonable statistical queries you have will only depend on low-dimensional statistics. And in practice, actually, what we find is that it's sufficient to just track the skills of individual players. So instead of tracking this exponentially large distribution of the skills, what we do is for each team, we track a very small thing. Okay, so we go from 5 to the 20 to 5 times 20. Okay, so we get something that we can sort of do in practice. And crucially, this is computationally feasible. I mean, it's something you can actually do. You can actually start to solve the problem. And what's also nice is that for the specific types of models that we talk about today, of course, you incur some statistical bias by neglecting these correlations. But if you do it carefully, the amount of bias you introduce is reasonably well controlled. Somehow, because the dynamics are already independent across individuals, and the observation model is not extremely informative, right? There's sort of a nice decay of correlations property that means that it's as safe as it is going to be, somehow. And so that is going to be the basis for how we're going to do filtering, smoothing, and parameter estimation. So for filtering, let's recall, so the object of interest is this distribution here, filtering distribution at time k, is the distribution of the skills at time k, given everything we've seen so far up to and including today. Right? Now, to compute this, every method under the sun essentially relies on two basic recursions. So one is the sort of prediction step, which is the following. So say I have my belief about what was happening yesterday, and I know the dynamics that take me from yesterday to today, then I can combine them to get my predictive distribution of what's happening today. Okay? It's somehow a matrix multiplication in the abstract. Right? So that's what this propagate step means. It means I combine yesterday's filter with the dynamics to get today's predictive distribution. And then, the second step is saying, okay, given my predictive distribution today and the observations I have today, I can get my filtering distribution today by doing a Bayes update, essentially, by conditioning on that likelihood. So that's what this assimilate step here means. It means combine the predictive distribution with the likelihood from today. Yes?
This filter definition does not match the filter definition but this is
yeah, so it's because the application I was talking about before, it's slightly easier to talk about conditioning on everything up until yesterday, but the usual definition is this one.
This is easier than the previous one.
So they're equivalent. If you sort of look at this first line here, you can go from one to the other very easily, let's say. But let me, to be clear, if you look in a textbook for what is the filtering distribution, it's what I've written up here.
So isn't this objectively easier than the previous one? The previous one was future prediction. This is not future prediction, in this direction.
So what I'm saying is, if you look at this first line of the two equations, this predict equals propagate, blah, 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 it says that you can go from a filtering distribution to a predictive distribution just by doing one step. So they're not substantially more difficult than one another.
But this implies doing the N matrix.
Yeah, I mean, for everything I do, I'm going to assume that.
So because in that sense, it's clear that predict is harder than filter, because predict requires an extra piece of information.
Okay, so both of them require knowing the system dynamics and the observation model. So it's not a distinction. And to clarify, to compute any of them, you are going to be doing these recursions in some form or another. They contain the minimal and maximal amount of information needed to do so, is the dynamics and the observation. We can discuss it later as well to sort of clear up the details. Okay, and so just to sort of point on the literature, let's say, is that most ways of doing filtering, whether you're on a continuous state space, a discrete state space, whether you're doing things exactly or approximately, you are really implementing these recursions in some form or another. Whether it's the forward algorithm or the Kalman filter or the particle filter or whatever it might be, this is really what's happening all the time. Okay. Now, for the smoothing distribution, it's a similar story. I won't belabor the point, but somehow, so this is your object. You fix your number of observations, capital K, and you're trying to compute the conditional distributions backwards. Now, by contrast with filtering, which is somehow a forward operation, smoothing is a backward operation. They're sort of two sides of the same dynamic programming problem in a way. And so to compute the smoothing distribution, there's again these sort of abstract recursions that you use. Essentially what is happening is, you look at your conditional distribution tomorrow, you look at your conditional distribution of today and tomorrow, and then you collapse back down. So I won't go into the details here, but again, it's sort of generic stuff. Every algorithm I know uses these recursions at some level of abstraction. Okay. And so when we look at specific algorithms, the question will really be, how do I do this step of bridge? How do I do this step of marginalize? But everything else is sort of universal. For parameter estimation, this one necessarily has to be a bit rushed relative to its complexity. But okay, let me sort of give the quick version. So the object of interest here is the marginal likelihood of all of the match results as a function of the model parameters theta. Okay. Now, this is often not analytically available. I think for all the models we talk about today, that will be the case. We don't have Gaussian dynamics and Gaussian observations, for example. So a common and generic strategy for doing inference in latent variable models, and in particular for doing likelihood-based estimation, is what's called the expectation maximization algorithm. Okay, and so at its core, the idea is, we want to maximize the log probability as a function of theta. So what we can do is we can write log p theta as a maximum of some more complicated functional, and then do joint maximization over the two of them. So it takes me possibly 2 hours to teach the EM algorithm to my undergrads. I'm not going to go into it in full details now, but the point is somehow it's completely routine. we understand what's going on really well. It's not an amazing algorithm, but it has lots of nice stability properties, let's say. For the purposes of today, the important thing is that what we're doing when we do the EM algorithm is somehow imputing the latent skills that we haven't seen on the basis of a parameter estimate, using those to improve our parameter estimate, and then rinsing and repeating somehow. So we alternate between computing smoothing distributions, using them to estimate parameters, and back and forth until we sort of stabilize. Okay, so this is sort of related to the earlier comment of to do good parameter estimation, you need to do good smoothing. It sort of comes up at this step. So, okay, that's all kind of generic. You know, that would be something you could teach in a basic course on state space models. But we have, again, this concern of working with factorial state space models, which makes our life a little bit harder. So let's talk about what scalability might mean for these models. So for lots of interesting sporting applications, again, for this very general definition of what sport is, we have many players, right? We have a large enough N that this tracking problem becomes challenging. We have many matches, right? We have lots of matches happening. This is extremely true for things like online gaming, for example, where the scale is huge, right? And additionally, something which we have to keep in mind is that depending on the sport, we can have very high frequency matches and they will be irregularly spaced, right? It's not everyone plays at the same time on a Saturday afternoon. It's, you know, I'm up at 10 p.m. and I'm going to play 7 games in a row and then go to sleep, you know, or whatever it might be. So we need methods that don't require lots of regularity in that sense, but that are a bit more flexible. And so the goal here is to focus on methods which, number one, we can implement online, right? We can do it in a streaming way because it's, you know, for some of the questions we have, the methods are completely uninteresting if you can't do that, okay? We also want a computational complexity which is linear in N and K, right? Somehow we know that the cost has to be at least N because we should look at each player at least once, and it should be at least K because when a match comes in, we should look at the result of it. And that would be the best we can do. We're going to see that we can actually keep the cost down to that. So it's sort of, that is what scalability means for these models, is you should have to look at each player and each match a constant number of times, and that will be sort of sufficient. I should say, you know, these goals, they apply particularly to smoothing and filtering. The parameter estimation question is a bit hairier, and we can discuss that in questions sometime. Okay, so how are we going to do this? So the thing that underpins all of these methods is to make what I'll call a decoupling approximation, right? And so for tracking player skills, and tracking here I mean is just a catch-all term for filtering or smoothing, you know, just approximating conditional distributions. Everything we do will make the approximation that the filtering distribution is approximately the product of the marginal filtering distributions. Essentially, we neglect correlations across players when storing them. And this is true whether we're doing filtering forwards in time or smoothing backwards in time. So again, the point here is that, you know, this can be provably sensible because we have models with nice weak dependence properties. And computationally, it's something we can really do and scale up very nicely. So let's talk a little bit about how that manifests. So again, I'm going to say some very basic things, but with very important consequences. So one is that for typical sports, not all of them, but most of them, at any given time, any player is playing in at most one match, right? You can't be at two places at once. Of course, this fails for things like online poker, let's say, but for sort of conventional sports, it's a very plausible assumption. Another one is that any match involves at most two players or at least some constant number of players, depending on how you're modeling things. It's not that as you have more players in the competition, each match sort of grows in scale, let's say. And so the consequence of this is that actually, when we receive the results of a single match, you know, these two teams played against one another and this team won, we don't have to look at the whole system. All we have to do is update our filtering distribution just for those two teams who were involved, right? And whatever's happening with the other teams is their business. So what does this look like in practice? So as a consequence of this, sorry, this is another point that's worth making. So on a given match day, we might receive the results of multiple matches, but we know they're going to be disjoint, right? 10 matches took place this weekend. There were 20 distinct teams involved. There's no overlap between each of them. And so what I can do is I can take each of those 10 matches, assimilate their outcomes in parallel without having to look across somehow, and I can get very quick updates as a result of that. Right, so I update our filtering distributions only for the pairs of players and matches in parallel, which is very sort of favorable for us. The same thing is basically true for smoothing, and it's actually slightly nicer, but it's not important to go into that. Okay? And so this sort of means that even though the system as a whole has a lot of dependencies, right, we can sort of carefully neglect them and have very low-cost updates. Okay. So we can then talk about what it looks like to assimilate the result of a single match. Maybe something to keep in mind is, we want our filtering procedures to be lazy in a way. We only want to update our distributions when we have new information, right? Rather than maintaining everything at every single match day. Okay, so what do? So when we receive the results of one match, we have our two teams who are involved. What we should do is we should go back to the last time they played anyone, the last time we looked at their skill levels. And those could be different times. Then we retrieve the filtering distributions of those players' skills on those distinct match days. And then we pull those forwards in time. Right? We say, okay, if their skills were like this at these due dates, I can follow the system dynamics and update to where they are today. That gives me my predictive distribution. Now I take the observation of today's match and I combine them with that distribution to get my sort of posterior for today, if you like. And then that gives me a two-dimensional distribution, right? It's the joint distribution over the skills of those two teams today. And then I break that apart into two one-dimensional distributions again. So just for a moment, I deal with something two-dimensional, which is sort of the most costly thing I can do in a way. And then I break it apart again. Okay. And that will sort of hint to you, okay, how could this become more expensive if I have multiple players in a match? Okay, so for the last bit of the talk, so there's two things I can do. There's one which is going through example algorithms, and then there's some sort of computational examples at the end. I think I will focus on the examples of algorithms so it's more illustrative, but we can talk about the numerics, if time permits or after if it comes to it. I think this is sort of better at getting the point across. So, okay. So there are many algorithms for treating this problem. I'm going to present some of them to you roughly in increasing order of how sophisticated they are, starting with very simple things and building up to sort of slightly more elaborate things. And the experiments sort of treat their practical performance. There's not huge surprises, let's say, but there are some trade-offs involved, let's say. Okay, so the first one I'll start with is what's called it's named after a man called Arpad Eller, but people always call it ELO, and they often capitalize it as if it's an acronym, but it's not. But in any case, it's sort of an extremely widely used method for rating the skill of chess players and increasingly other sports. Okay, and so what do these updates look like? Oh, sorry, what is the model here? So it's not really fully specified as a statistical model, but somehow the idea is you model each player's skill as being a real number, okay, and you model the outcomes of matches through a logistic regression, the difference between skills, and then squash that into 0, 1. And so what happens is you receive the results of a match, and then comparing the predictions to the observation, sort of increment the skills upwards or downwards as you would like. And so it looks something like the following, right? So the home team's skill goes up if the home team wins, and it goes up by a lot if the probability of them winning before the match was very low. Okay, so you sort of look at the surprise between the two and increment on the basis of that. You see from this that you have sort of conservation of skill. The amount that one goes up by is matched by the amount that the other goes down by in total. Okay, and so this is not a filtering algorithm per se, but you certainly have a sequence of skill estimates over time, and so you can use it in that way. There's a nice interpretation of this as sort of doing a stochastic gradient descent method in an online way. You can sort of look at each of these terms as the gradient of a certain log probability. Okay. So this is unbelievably widely used, and despite the way I've presented it, you can sort of write it in a way that requires you to know very little maths, which is probably one of the reasons it's so widely used. Let's say you can do it by hand if you like to. One thing I find super interesting, so this little eta out in front of the updates here, you will recognize that as a step size or a learning rate or something like this. Something I find very interesting is that from one sport to the next, this factor is very different. Okay? For chess, it's one thing. For football, it's another. For League of Legends, it's another, and so on and so forth. And actually, it's done in a pretty heuristic way somehow. It's done by a human having a look at what happens if you change the model. So it's very plausible that it should be different for different sports. What I find interesting is actually when you put your statistician hat on, or whatever inference you like to think of, it's really a hyperparameter selection problem, and you can be very principled about it. You don't have to have someone tuning things by hand, but you can write down a marginal likelihood and maximize it or something. But okay, so this is sort of the starting point for many of these methods. Yeah, so just at its core level, it's sort of a stochastic approximation. You compare the observed outcome to the predicted outcome and use that to update things. And so a natural thing to do, particularly if you're interested in filtering problems in general, is to say, can I make this a little bit more statistical and do something sort of principled? And so that's what Mark Glickman did in the late 90s. So he did, his model is nominally kind of the same, but he's going to really treat it as a Bayesian filtering problem. So instead of tracking skills with a point estimate, he's going to approximate skills with a Gaussian distribution. So now you have a sort of mean and variance, if you like. Now he really writes down a model for the dynamics. So the way that your skill changes over time is just a continuous time random walk with a Brownian motion, and you have the same observation model. Now, let's go back. So what do we need to specify these models? We need to know how to do propagation and assimilation. Right? And so the propagation step is very easy, because if your filtering distribution is Gaussian, and you know that the dynamics are adding Gaussian noise, then computing the predictive distribution is very easy, sort of closed form updates by Gaussian conjugacy, if you like. For the assimilate step, we don't have the same luck, because the observation model isn't Gaussian. And so what we do is sort of what people would call the extended Kalman filter, or the Laplace approximation, or whatever you might like, which is somehow that you take this likelihood, you do a Taylor expansion in log space, and then you do an exact update for that approximate likelihood somehow. So it's just sort of looking at the mode of the conditional distribution and fitting a Gaussian to it. Okay, and again, that's something you can do very quickly. And so one thing that's nice about Glicko that you couldn't do with ELO is you can now actually ask the question of what is the smoothing distribution? And if I look backwards in time, what was going on back here? The question doesn't really make sense for ELO, because you're not tracking a filtering distribution, you're just doing point estimates. Whereas here you can be principled about that, you can fit model parameters through EM and so on. So it's, in terms of what you implement for your algorithm, it's probably different by 1 or 2 lines, but you very quickly have interesting statistical questions you can answer now that you couldn't before. Now, there's another method called true skill, or true skill through time, which was used actually for the Xbox for many years as a way of rating player skills there. Again, if you think about that for a moment, the scale of that problem means you need to have good scaling with respect to the number of players and the number of matches. And if you look carefully, it's almost identical to the previous slide. Okay, the only things that have changed, we have the same model, except we change our observation to a provert regression rather than a logistic regression. We pass it through a Gaussian CDF rather than a more typical sigmoid. And so why is that useful? So we do propagate in exactly the same way because of Gaussian conjugacy. For assimilation, instead of doing a Taylor expansion, we do a sort of moment matching step instead. And the reasoning behind that somehow is that the Laplace approximation, it's very well behaved when the distribution you're approximating is very symmetric, right? This is sort of morally plausible because you're making a Gaussian approximation. Whereas for these binary regression observation models, you often have very skewed likelihoods. Right? The whole point is that it's 0 over here and 1 over here, let's say. But somehow the worst case for these things in a way. And doing something a bit more robust based on looking at posterior means and variances might behave better. And so that's sort of the principle of what they do here. But otherwise, it's conceptually the same model with a marginally different likelihood, treated slightly differently. Okay, so there's 2 more examples I'll give quickly and then wrap. So one is, so these models I've shown so far, they have to do approximate inference because you're not tracking the distributions fully, you're sort of making a parametric approximation. Now, if you're interested in getting sort of slightly finer details on the tracking distributions, one way of doing things is to use a particle filter, basically what I would call sequential Monte Carlo. And so the idea is instead of representing the tracking laws with something parametric, we just use a collection of synthetic particles to represent this distribution as a bunch of point masses. Now, what's nice about this setting is that it's so flexible, right? You can handle any representation of skills, you can handle any dynamics you like as long as you know how to simulate from it, and you can handle any observation model you like as long as you know how to compute the likelihood, okay? The downside is it becomes a stochastic method, and so there's various considerations one has to be a bit careful about that. But in principle, that's very nice, right? So the propagate step is just treated by simulation, right? You just have your distribution, you have your points representing the filtering distribution, you sample from the model to get your predictive distribution. And the assimilate step is done by importance weighting with a bit of sampling. So sort of very easy to implement stuff. And that's sort of, the only stochastic method we describe, I think. And then a final example, which is really where the project started from, which is we were interested in solving the problem with discrete tracking distributions. So representing skills, again, as I said, there's a number between 1 and 100, just a whole number. Now, what's nice about this is you can represent the tracking distributions exactly. It's just a probability vector of length 100, so you can safely store that, right? And so, if I take my dynamics as coming from some continuous time Markov process and my observation is whatever I like, Actually, the propagate step is closed form. Right? I have a finite vector telling me a probability distribution. I have an S by S matrix telling me what the dynamics are. So to get my predictive distribution, it's just a matrix vector product. Right? It's linear algebra, it's as fast as you like, and it scales very nicely. In practice, there's also a matrix exponential involved on top of the matrix multiplication, but it's kind of a detail. Moreover, doing the assimilate step is closed form as well. Right? If I have a probability vector and I have a likelihood, which in this context is also a probability vector, I obtain the posterior distribution just by multiplying these element-wise. Right? So that's very easy to do. And so what's nice for this setup is that there's no systematic bias in the method. There's no sort of parametric approximation or stochastic approximation aside from this decoupling approximation, that we only track individuals rather than joints. But as I've sort of hopefully made the case for, this is pretty critical for having an algorithm you can even implement rather than doing anything further. Okay, and then in the paper we have this sort of nice little table that characterizes, what are the differences between them, what are the trade-offs you're making through these different approximations. Somehow, you can do very cheap things like ELO, which allow you to make more restricted probabilistic queries, or you can do these richer things like SMC and discrete state spaces where you can answer more elaborate questions quite easily. Okay, so I had some sort of numerical experiments at the end that I can talk through. They're largely sort of testing the intuition for these methods and seeing what comes from them. But I'm worried that I've hit about 50 minutes, so I'd like to ask what the best thing to do is. Is it best to wrap for questions? And then we can... I can do it in 5 if that works. Okay, let's do that then. Okay. So, yeah, we're doing some case studies here. The story is not that we have the greatest algorithm in the world, but rather that we have the flexibility to do things we would like to do, and things behave as expected. And by the sort of principles we've described, we expect things to scale up nicely. Okay. So yeah, we want to replicate a realistic workflow and show that the different parts of that work nicely. We evaluate some different models, both qualitatively and quantitatively. We do a few sort of case things. So one is, we take a model where we have static hyperparameters, which we assume are well fit, and we just track that the filtering and smoothing makes sense there. Another is that we show that based on historical data, we can estimate the parameters reliably. And then finally, we sort of use filtering and smoothing for more applied problems, doing prediction and doing evaluation. And yeah, okay. So there's a nice GitHub package that Simon Lorenzo wrote, which has got all the experiments and is pretty usable, I would say. Okay, so the nice starting example is the following. It's looking at the Argentina national football team in the build-up to and across the 2023 World Cup, I think. And so what we're looking at on the right here is the sort of tracking distributions for the skill of the Argentina team from one game to the next. And we've implicitly fit all the other teams as well, but we're focusing on Argentina because they won, basically. And so we see that before the tournament, they have a sort of a skill rating that's reasonable, let's say. In the first match, they lose to Saudi Arabia. Now, for football fans, this is a big surprise, right? And so we see that in every one of our filtering methods, there's a sudden jump down in the skill tracking because everyone's saying, oh my God, what's just happened, basically. And then they go on to win, 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 draw, win, and draw, and things sort of go up or flat as we would expect. Okay. Now, you see for ELO that you have a very impoverished representation of the skill distribution. You have a point estimate, you don't know anything about the uncertainty on top of it, and you have no facility for computing smoothing distributions. So it's useful, but it's quite limited. If we look at the others, we see that, so in all of these, I think purple is the filtering distribution and green is the smoothing distribution. We see that the filtering distribution is pretty reactive and jumps around quite a bit, and the smoothing distribution is rather more flat. It sort of says, with the benefit of hindsight, actually, what happened against Saudi Arabia was just kind of noise. And we don't need to adjust our beliefs about the Argentina football team too much in view of that. Yeah, we see for true skill, which is the sort of Gaussian approximation, you have sensible-looking Gaussian tracking distributions. For the SMC methods, what you're seeing basically is a histogram of particles. So you see the Monte Carlo noise pretty explicitly, but you're tracking the shape of the distribution pretty reasonably. And for the discrete model, it's a bit interesting. So I think because the state space is taken as large as it is, you really can't tell the difference with a Gaussian distribution here somehow. But really under the hood, these distributions are all very fine histograms as well, but they sort of behave reasonably. Okay. Yeah, so we see that when we go forwards, things are very reactive, and when we go backwards, things are sort more smugly saying that they knew what was going to happen the whole time, let's say. And I'll talk quickly about this tennis example here. So this is looking at women's WTA tennis over a 4-year period. What you're seeing on the right here is the log likelihood surface that we estimate using different methods. Okay, so we're trying to do parameter estimation, essentially to estimate things like how quickly the player's skills change over time, how noisy is the result of a tennis match, and so on and so forth. What we see is that in each case, the parameter estimates converge to roughly the same part of the state space. So even though we're using different nominal models, there is some way of translating between them rather roughly. You'll see that there's no ELO here because the question doesn't really make sense for ELO. What we also see actually is that in the true skill case, right, where we're making this Gaussian approximation to the filtering distributions, there's a bit of additional bias in the model that means we don't quite capture the mode as we would like to. Whereas for the SMC, even though we have this Monte Carlo noise, we do reliably get much closer to the mode, and for the discrete model, things are even better somehow. So that's sort of a nice strike in favor of it. I'll pass over. This one's fun, so I'll do it now. So this is so one of my co-authors, Sam, is a big football fan for Tottenham Hotspur. He's been sort of suffering for many years as a result of that. And so the case study here basically is to look at the impact of the manager of the team over time. Okay, so these sort of vertical lines are sort of change points in that respect. And so the idea was, okay, with the filtering law, we can see maybe what public sentiment around the managers might have been in time. But when we compute the smoothing distribution, things stabilize quite a bit. And we can see, the Pochettino in the middle was maybe credibly really improving the teams, but the other managers, the shifts were more negligible somehow. But getting rid of people may have been premature, let's say. And so this is sort of not a completely credible way of doing the retrospective evaluation. In principle, you should include effects for who the manager is and so on. But at least to first order, it tells a bit of a story. Okay, so let me just wrap. So yeah, the focus of today has been to look at the skill rating problem and explain how we can sort of solve it by making working with these nice factorial state space models and using their flexibility to treat very general dynamics and observations, but using the nice sort of simplified algorithms to solve them in each cases. We want to set things up so that we can do filtering, smoothing, and parameter estimation in a nice integrated way. So they sort of use the same primitives. What's nice is that by taking this model-centric approach, there's various ways of extending the model. So what I've shown you is sort of the simplest models you could come up with, but there's all sorts of additional information you can include. You can include sort of extra covariates and context about each match. You can have richer observation models. So in the paper we have an example with sort of Poisson goal model for football. You can include sort of random effects to add in extra stochasticity for each observation. And you can include things like multivariate skill representations. So a very common thing in the quantitative analysis of football is that you model teams as having an attacking skill and a defensive skill. And you can think of various ways you could cook that up into a likelihood and a dynamics model. Yeah, and then because I'm sort of often thinking about algorithms, there's various interesting algorithmic extensions that I'm sort of softly interested in that would make things more credible and more scalable. But I'll stop talking there, and apologies for running over slightly. Thanks.